we've been doing for quite some times, like in our labs, especially on how to thinking about the scaling of robotic manipulation through two major lenses. The first one is structured word models, and the second one is how to do structured tactile sensing to give the robots some more detailed understanding about its interactions with the environment. So recently, we have really seen tremendous amount of progress in the field of robotics. For example, humanoid robots has really been like dancing around, moving around. We have also seen a wider and wider deployments of self-driving cars. But what about complicated physical interactions with the environment? So how far are we in actually achieving human-level manipulation capabilities? You are in academia. You probably have seen many like very interesting robotic demos, but whenever you go to any of the industrial expositions, for example, Automate, ProMat, you'll be amazed at how many perfectly shaped boxes you'll see. But that's the current state of the industry deployments of the actual robotic systems, where the robots are mostly still handling relatively simple objects with relatively simple motions. But what we want the robot to do are much more than that. We want the robots to work not only in fully structured environments, but semi-structured environments and unstructured environments, handling objects that are not just rigid, but deformable, like fluids, clothes, ropes, cables, and everything. We also want the robots to not just handling a short horizon task in a restricted environment, but long horizon tasks in a larger scale environment. This actually requires a level of generalization and adaptation goes beyond the current reach of the robotic systems. So people are thinking, yeah, can we then like borrow some of the successes from the foundation models in the language domain and vision domain and pour them into the robotics? So that's why there has been a lot of like interest and excitement and capitals pouring in developing like foundation models and foundational robotic models. If you categorize like those investigations, sort of you can categorize them into like two categories. The first one will be take use of the current existing vision and language foundation model and try to see how some of those foundation models coupled with some of the things we know about robotic systems to make the robots work better. There has been very good examples like GPT, SAM, Dino, foundation stereo poses. Those can actually be very useful to integrate into some reasoning and perception systems for our robots. Some of our earlier work involved, for example, Vox Poser, allows the robots to take in natural language instructions and work with an open set of objects for this tabletop manipulation tasks. And another thread I would categorize is as these directions of robotic foundation models, which instead of thinking things in a more modularized manner, they are trying to learn this model in a more end-to-end fashion. Generally, like people currently see two general threads of doing this robotic foundation model. The first thread is taking the success from the vision foundation model, language foundation models, and fine-tune from these vision language models. People call it vision language action models, large behavior models. There has been many names for it. And there has also been a lot of success stories over the past few years. Another thread is instead of pre-trained on vision language tasks, people pre-train it on video prediction tasks or words model prediction tasks. Like Ani actually had a very nice series of blog posts on Twitter. I'm a big fan of those posts, trying to tell you more details and nuances in understanding these directions on what does it mean for those word model and what's their positions in the context of this general purpose robotic capabilities. But still, given all those existing investigations, there are still a lot of unanswered research questions. For example, steerability. And what does it take and how much additional effort does it actually take for you to steer the robots to do another task? Some of the promises in the vision language action model domain, people say, oh, you just give the model another language instruction and the robots will be able to do the new task. But in practice, the model may not actually listen to the language instruction. Most likely, it will do whatever it thinks makes the most sense, just given the visual observation. Steerability is actually a huge issue for all of those existing models. The second one is about physical grounding. Either for the vision language models, which mostly are trained with many language tasks, it doesn't really have very good understanding about the physical interactions. Similar things with the word model or the video models. The grounding between the video hallucinations and the actual physical execution of the robots, there can also be a huge gap there. There's also an issue about debuggability. If things go wrong, now what? If the robot is not doing what you want the robot to do, what do you have to do in order to correct the model? If you have the budget to collect maybe 10,000 more demonstration data or corrective data, where should you collect that data? And how should you set up your expectation in understanding the performance of the robots as a result of those data collections? Those are also unanswered research questions. And obviously about scalability. What if we move the whole system into larger scale environments or longer horizon tasks? Those are still unanswered research questions we are trying to actively answering right now. So for many of these directions, I wouldn't never bet against it, but I would be cautiously optimistic about the future prospects of many of those directions. And people should calibrate their expectations through this kind of scaling up efforts, because there's a lot of nuances in just hearing the hype and hearing the excitement. And then when we look back at the current foundation models, what my lab's job is really trying to identify what the gaps out there and how should we contribute in bridging those gaps, especially between the current foundation model and the robot's physical interactions with the environment. I'm really looking at it from like 3 lenses. The first one is actually sensing. So many of the current foundation models, they're trained only with language data or vision data. But one of the most important missing piece is actually our understanding of touch. So tactile sensing plays a very, very important role for us to make physical interactions. And looking at this image, just from the image, it's very hard to know whether this is a tight grasp or a loose grasp. Only the tactile sensing from the interaction can tell you how much force you are actually applying. Or you are sitting there or standing there. How do you know you are sitting or standing in a stable posture? So it's a tactile sensing from your body that tells you you are sitting or standing in a stable posture. This is the type of sensory data we take for granted, but it's not there yet for our current developments of robotic models. So as Tom also mentions, during my PhD at MIT, we had this Nature paper where we developed a tactile glove, where we give this glove advanced tactile sensing capabilities over the palm area. On the left is the interaction. On the right are the visualizations of the tactile signals, where the thickness of the dots telling you where you have contact, how much force. You can also see these circular contacting patterns when you are pressing on the rim of the mug. So this sensing mechanisms is actually very simple. We built this tactile sensing through this what we call piezo-resistive material. The property of this material is the larger the force, the lower the resistance. And then you can have a readout circuit to read out the tactile informations through the changes of the resistance. Back then, we used this tactile glove to do tasks like object recognitions. And through which we actually collect a large amount of hands-object interaction data. And then we actually did something very interesting. We want to see how humans are actually using their hands. This is the visualizations where you can see a mouse hovering on different parts of this hands. And you can see like the color of the dots actually indicating how likely that dots will be used together as a hovering dots during those interactions. So that's why when you're hovering the mouse on the palm area, you can see all the dots near the palm area were light up. That shows the areas near the palm areas are more likely to be used together. And when you're hovering the mouse, for example, on the fingertips, you will actually see even if the fingertips, they are far away from each other, they are also more likely to be used together. That shows some signatures and patterns of how humans are using their hands, which is going to be very useful for us to design our tactile sensors and also prosthetic tools or end effectors like down the road. And this glove is currently collected by the MIT Museum. This will be the first thing you see when you enter the AI section of MIT Museum. It's close enough whenever you get a chance to go to Boston, highly recommend. And going from there, we have really been thinking about, like, instead of just understanding human, can we really using this sensor to benefit and enable the capabilities for our robots? So through this lens, we have made investigations along 2 major threads. First one is how we can build like simulations in order to simulate these tactile signals, be able to scale up the data through the digital world. And second, how we're going to scale up the tactile data also through the real-world data collections. But first, let's making sure the sensor is useful for robots. So as I started my lab, we basically improved upon the sensor, make the sensor higher resolution, better signal to noise ratio. And most importantly, it can be integrated very seamlessly with the robots for the robots to do interaction. And together with imitation learning, we allow the robots to do various of different manipulation tasks autonomously. Here, what you're seeing here is this robot go to reach into a bag, grasping a grape, and then place it onto the plate. You can also see the signals on the screen on the back, which shows the real-time visualization of the tactile signal. Besides cases that involve visual occlusions, we also allow the robots to manipulate fragile objects. You can see there's a person perturbing the robot from doing the job. The robot knows to recover from their perturbations because it knows there's no signal between the fingers, such that it knows to redo the grasping. And the third one is actually to do some in-hand reorientations. You can also see the tactile signal in the back screen that shows the tactile sensing gives you the precise estimation about the position and orientation, obviously in an implicit way being taken into account by the policy for this manipulation tasks. And the last one is some bimanual coordination. So then you might be curious, what happens if you don't have the tactile sensing? Here, we are actually showing baselines. If you don't do any tactile sensing, using exactly the same data and only the visual observation. For the hex key reorientation task, the robot can still do something that's seemingly reasonable. But in this case, missing by a little bit actually means missing by a lot. So meaning without the tactile sensing, the robots are not as focused or not as sensitive to the precise locations and orientations of the hex key between the finger. And in the grasping grape example, without the tactile sensing, it either didn't grasp anything, or it might apply too much force and might accidentally break this fragile fruit object. And one interesting note I want to mention here is that during the data collection, you might ask, yeah, the robot is getting the tactile sensing. How about the teleoperator? Is the teleoperator getting this kind of haptic feedback? In our case, we didn't use the actual force level feedback, but we actually will visualize the tactile signals during the interactions. So we call it visual haptic feedback, which turned out to be very, very useful for the human teleoperators in be very fast and very efficiently to do the task and do the task in a more consistent manner. Question?
Just a quick clarification. The previous videos had with cameras that were provided as input to the policy.
Yeah, we have cameras. We have external cameras also looking at the environment.
Oh, no, sorry, I meant the lens camera. Cameras on the.
Oh, we didn't use wrist mounted camera for this specific case. For this project, we use the point cloud observation together with tactile sensing. We fuse them all into the unified 3D representation space and using a diffusion policy and taking into point clouds using that architecture to do the policy learning.
I guess I'm curious how much you think the results would change. One of the standard arguments for why we don't need tactile is just put wrist cameras. I'm curious if you have some calculations with cameras or some intuition for how much it would happen.
Very good question, Ani. So the question was about what if you have a wrist mounted camera? In those cases, how much does touch help? So I'm going to show a video actually later in the slides. So in this case, we have this is actually similar to a Yumi setup, but with tactile signals. So you can see on the wrist, we have this kind of GoPro camera. And on the bottom, we have visualizations of the tactile signals. Here, the task is trying to do reorientations of the testing tube before you can do the insertion. And there is a person constantly perturbing the robot from doing the job. And the robot knows to recover from that external perturbations before it can do the insertion. And on the right are actually videos that are exact inputs to the policies. We have already reoriented the camera such that it can see the testing tube. But still from the video, it's clear that the testing tube, because it's transparent, it's still very, very hard to understand the precise orientation and the positions of the testing tube between the fingers. But you can see the tactile signals on the bottom. It gives you a very precise description about the position and orientations. You can see that in the middle, there's a person constantly perturbing the robot from doing the job. And the robot knows to keep recovering and recovering from that perturbation. And only until the testing tube is upright, it knows to do the insertion. So in this specific case, we also observe tactile signal is very, very important and essential for the success of the task. Okay, So this is about like a haptic feedback. We find like given the visual haptic feedback to the teleoperator, not only makes the success rates of the teleoperator higher, also making their behaviors more consistent, but also actively at like establishing the causal relationship between the tactile signals and the actions that you want the robots to execute. And our sensor actually, many people actually ask like, yeah, your sensor seems to be good, but how about the resolutions of the sensor? Like how much resolution is actually enough for this type of sensor? So for our sensory design, the distance between adjacent sensors is like 2 millimeters. And we actually goes back to some like earlier studies, some very classic studies about like humans' haptic perceptions. And this is an interesting study to understand at different parts of your body, like what's the tactile sensitivities at different parts. And one of the classic like testing people do is called 2-point discrimination. So basically how the process works is that you have 2 needles touching different parts of your body. And they are asking how far these 2 needles needs to be away from each other. Will the person tell this is actually 2 needles instead of 1 needles? And then measure the distance. And if you look at the fingertips, it's almost exactly at 2 to 3 millimeters. So meaning our tactile sensor is actually have comparable like tactile sensing resolutions as humans' fingertip. And actually the most sensitive parts of your whole body is not your fingertip, it's actually your lip. And because our lab has really been benefited from many of the open source hardware projects, so we are very committed and actually release a very, very detailed full reproduction guides of our tactile sensors. And those was released like a little over a year ago. And a year later, our sensor has been used across like many different institutions, both within academia and also in the industry. And we have already seen a series of work that's built on top of our tactile sensors for various of different very interesting manipulation tasks. And a few days ago, I was actually at GTC. Our collaborator, Analog Devices, they actually is already trying to commercialize our sensors and integrate our sensors with their like grippers and also dexterous hands in order to do this kind of fine-grained manipulation tasks for cable manipulation and sockets manipulation. And I also want to provide a little bit of summaries in how we position our sensors in the whole like fields of tactile like sensor developments, because there's a bunch. Like tactile sensor hasn't been as converged as, for example, vision sensors. There has been many other sensors like optical-based tactile sensors, magnetic-based, capacitive-based. So my very, very first research projects when I started my PhD at MIT was working with gel sites, which was an optical-based tactile sensor. Several key benefits of our sensor is about scalability. It's very easy to scale our sensors into larger areas or smaller areas. Back then, we even have a tactile like a carpet in order to do like a larger scale like measurements of these contacts. The second one is about like this kind of flexible like nature of our sensor. Because our sensor essentially is just a piece of paper. You can bend it, you can twist it, you can cover this kind of deformable surface of a human hand. And third nice thing is about customizability. We actually already on the roads of customizing our sensor into different form factors and different shapes, like fingers of different shapes. And also here, some kind of robot skins, and also the tactile glove. It's very, very easy to just customize our sensor into different shapes and different form factors. And next one is about robustness and consistency. This is actually my major complaint about those optical-based tactile sensors, because many of the optical-based tactile sensors, they built using rubber, and rubber can lose properties over time. It has just so much like headaches working with gel sites, gel slim, and the soft bubble grippers from Toyota research because of the driftings of those kind of rubber materials. But our sensor is incredibly robust. One data point I can give you was my students who built 4 pieces of sensor for NVIDIA during the summer of 2024. And the sensor is still fully functional and being used today. That shows the robustness and consistency of our sensors, not only over times, but over different fabrications of the sensors. And the last one I want to highlight is about the compatibilities of our sensor with simulation. So through the directions of scaling up like the digital data, we actually have already built a simulation for our tactile signals. Here on the first row shows like the interactions and some kind of characterizations of our sensor. And on the bottom, we show like how things are actually working in the simulation. So we basically build a very, very simple like spring damper and mass models that is able to render the tactile signals to show the state reading from the simulator. And here is a side-by-side comparison. On the left is a policy rollout of a robot like trying to like do this kind of bimanual assembly task. And on the back, you can see the visualization of the real tactile signals. And on the right is actually the simulated tactile signals by running exactly the same policy, also in the digital environment. You can see qualitatively how well aligned they are with each other. And besides qualitative measurements, we also do quantitative measurements. Here on the right, you can see this histogram. What the histogram shows is basically we use a teleoperator, collect a bunch of data in the real environments, and we replay those motions also in the simulation. And we collect all the tactile signals, both in the real environments and in the digital world. And we plot the histogram. Here, the blue like bars shows the real signals, and the orange bars shows the simulated signals. You can see how well aligned they are with each other. And this is very important because we all know if you want to work in the simulations, you have to do domain randomizations to do the sim-to-real transfer. But the more precise you can do SysID, the less randomization you have to do in simulation, and the more precise your robots will be when you transfer to the real environments. And for this task, we actually evaluated our framework both in this tabletop Aloha setup in my lab and this half humanoid setup at NVIDIA. So here are just some very typical visualizations of how you can do like a simulation, like reinforcement learning, fine-tuning in the simulated environments. And the fine-tuned policies will actually be able to like handle variety of different kind of assembly tasks so using the assets we borrowed from the factory like benchmark. So these are some of the manipulation like trials using the robots in my lab. And here are some additional manipulation trials like using the robots at NVIDIA. Shows if you have a digital world, you can actually have this very scalable ways and generalizable ways of working with robots of different form factors. And one interesting thing I want to highlight in this procedure is not only the sim-to-real gap, but the real-to-sim gap. Because for this specific project, what we did was we first collect a bunch of demonstrations in the real environment. Then we train the policy. The policy can maybe give you like a 40–50% success rate. And then we port the policy into the simulation. You can also see a slight drop in performance because of the real to sim gap. But in the simulation, we can actually like fine-tune the policy using reinforcement learning, actually DPPO, and then like boost the performance up at a very high performance and then transfer to the real environment. So you can see from the real to sim, there's a performance drop. And from sim to real, there is another performance drop. But still, because of the fine-tuning you can do in the simulation, the overall performance will still be noticeably higher. So sim-to-real gap still exists and can degrade performance, but RL fine-tuning can significantly boost up the performance. And touch is actually essential to unlock the last bits of a performance through this reinforcement learning procedures.
Would it be better to collect demonstrations in sim?
So that is actually a very interesting point. The question was like, what are some of the considerations when you do the teleoperation in simulation? What our finding was sometimes teleoperation in simulation is actually harder than doing teleoperation in the real environments. Because in the real environment, you can just like move your head around, like looking from different angles. You also have a lot of like multimodal cues, the audio cues and some kind of vibration cues from the robots. Those are actually very useful, like for the teleoperator to do the task. And many of those information are like stored indirectly through these visions, like such that people can infer those informations. But when you do teleoperation in simulation, you don't have those. So sometimes that actually can create huge trouble for people to do the teleoperation. But again, that's a plausible way of doing it. And because you have a simulation, there's many ways you can improve upon some even like worse teleoperations to begin with in the simulated environment.
I have another question.
Yes, please.
Have you noticed any bias within the road to sim? Like, do the simulation show like less forces than typically you would apply in the real world?
So this is a very good question. So that is exactly why we have to do calibration. So here on the right is actually shows the profile of the force reading. So basically, this actually is borrowed from the idea of how do people do like white balances matches between different images. So basically, you have this kind of like histograms. You have the histogram like describing the statistics of the tactile like force informations, both in the real data and also in the simulation data. And then we do system identification by optimizing the parameters like KP, KD, and also some penetration depths in our tactile models in order to like making sure the force profile, they match with each other. Does that answer your question? Okay, so besides scaling up the simulation data, we're also looking to how we can scale up the real data. So that is why like rooted from this investigations of the universal manipulation interface from Shuyan. So we try to like bridge some very important missing pieces from UMI. So if you think about UMI, like for people of you who are familiar with this, essentially you have this handheld gripper that has some kind of mechanical spring. When the human operator do the data collection, you have the haptic feedback. So the person actually can have this understanding about how much force you approximately have applied during the interaction process. But that information was never stored anywhere in the original UMI design. The original UMI design only store the visual information and the position informations of the gripper. So it actually will be very limited when you want to apply the data to tasks that's like needs force. But our tactile sensor essentially bridges that gap. So basically, we store the haptic information the person is getting in an indirect manner using our tactile informations through the interactions with the environment. So similarly, we design our like a gripper to be very portable, and you can just hold the grippers and go to in the wild environments. And we have collected a bunch of data in the Columbia campus, both in the indoor environments and outdoor environments, where we have this kind of synchronized data, where the first row shows the visual observation, and also we show the second row the synchronized tactile information. So basically, we take this data to do pre-training, and then fine tunes with some kind of additional demonstration data in some specific task of interest. Like this was one of the tasks we did, where we will be able to use this kind of setup, trim policies that is able to do this kind of in-hand orientation tasks that involve fragile and transparent objects. And similarly, we have also shown with this kind of setup, we allow the robots to do in-hand orientations of this pencil, and then we can do the insertion of the pencil into the pencil sharpener. And then we actually are also highlighting tasks require force modulations. In this case, we want to suck some fluid up from the container. During the suction procedures, you want to release the gripper because you want to get some fluid up, but you don't want to release the gripper too much such that you drop the glassware. So that is exactly a type of task that require very precise force modulation. And last one, and not surprisingly, also trying to do some kind of wiping in order to apply the constant amount of force during this kind of wiping procedures. So these has been some of our investigations on scaling up the tactile data. So basically, we build these tactile sensors and also improved upon the tactile sensors to make it as easy to use and as democratized as possible, and be able to scale up both through the digital environments and also through the real world environments. We have also be able to apply our tactile sensing mechanisms into different form factors to starting to create this kind of ecosystems where everybody is able to design tactile sensors of different form factors and attach them into different ND factors of the robot skins or anywhere for us to scale up the tactile data for us to go towards this more foundational understanding of the physical interactions. So that is the first missing piece we identified. And the second missing piece is actually about the robot's understanding about the dynamics of the environments, or now the fancy words world models. So we humans can actually have this very strong intuitive models of the world. We can predict how the environment is going to change when we apply a specific action. For example, how the dough will change its shape and how the onion pieces will be moving around. And it's exactly this forward predictive capabilities. It allows us to do inverse planning or do corrective behavior planning that take feedback from the environments and be able to do tasks that are robustly in the real world environments. This is essentially a predictive model. And if you think about the construction of such a predictive models, there is a spectrum. On the very left are this kind of pure learning-based approach. So that is what's actually the canonical definitions of word models, where people are doing action conditioned video predictions. A very good example will be Genius 3. It's obvious they have been trained the model over a huge amount of, I'm guessing, like gaming data from the appearances. But most of those videos are still more or less in the navigation domain. And because they were trained on game data, we know game data is not accurate from the physical measurements. So those models may not describe the physical interactions as precisely as you need. And the other ends will be more physics. NVIDIA Warp and Newton, there are some very good examples of building the digital environment and simulation from the first principles, like F equals ma, and to build the digital world. But the issues with this direction is you need a full state of the environment. And you also need to assume you have the full knowledge about the governing equations of the dynamics environment, which is sometimes an assumption that doesn't hold when you face complicated real world environments. Then the questions we are trying to answer is, are there anything in the middle? Are there anything we can develop in the middle over the spectrums that get the best of both worlds? So one very important thread of the work that we have been doing is to use a graph-based neural dynamics model built on top of particle representations of the environment. We call it graph-based neural dynamics to model a diversified set of objects in the environment, including rope, closed, stuffed animal, multi-object interactions, and also this Best System Papers Awards, where we use this particle dynamics model to represent this elastoplastic objects like a dough. So essentially for particles, what you do is to decompose the objects into a bunch of spheres. And then we will have edges connecting between the spheres to describe the interactions both within an object and of course different objects. And the model we use is actually some graph-based neural dynamics models, where we have the descriptions of the current states, Z, that essentially is a graph. It contains a number of nodes and a number of directed edges. And then for each directed edges pointing from B to A, we will have an edge encoder that takes into account the information from the sender B and the receiver A to derive some edge representations. And then for each node in the graph, we will aggregate all the representations on edges where node A is the receiver. And we'll be able to update the representation also on the node A. And we can define arbitrary objective functions. In this case, we care about the evolutions of the environment. So we will supervise the model according to how precisely it can predict the evolutions of the environment. And because the node encoders and edge encoders are shared among all nodes and all edges, so you can naturally generate systems that are larger or smaller than during training. So back then, we showed it is able to model fluids fall down and merge with each other. On the left is the ground truth. On the right is our model's open loop future predictions. We'll be able to model fluids elastoplastic objects and also capture waves of fluids, etc. So then we are also seeing how it can also be extended into modeling real objects, go beyond just simulation. So it can actually be quite straightforward. You take observations of the real objects, and then you can approximate them using a graph. And this graph can be used to describe different substances or different parts of this object. You can have edges connecting between them to give the model this inductive bias in capturing the overall structures of the objects. And one of the most complicated objects and tasks we did was to use this model to model the dynamics of plastisms or dough for the task of dumpling making. So here is actually our setup. So we have 15 different 3D printed tools for the robot to select from. We also have 4 RGBD cameras looking at the environment. And in the middle, we have this red circle describing the workspace of the robot. And to learn the model, we didn't use any simulation at all. All the data we need are data we directly collected in the real world environment. So basically what we did was to take a tool, obviously you have to design some kind of primitive space for that specific tools and do random explorations over that primitive space in the real environments and collect the data. And using that data, using exactly the same graph-based neural dynamics model I described, we'll be able to learn models that describe how the shape of the dough will change when you apply a specific action using a specific tool. Here, the first row shows our model's open loop prediction, and second row shows what actually is happening in the real environment, where the blue spheres are describing the overall shape of the dough, and the red spheres are describing the shape of the tools. It also applies to many other tools like pressers or rollers, where our model can very accurately predict how the areas of the dough will be enlarged when you apply this kind of rolling action. And putting the things together, we allow the robot to do this incredibly challenging and long horizon tasks. And even during the process, there's a person constantly perturbing the robots from doing the job. We robotics just love to mess up with our robots and show how the robots can be robust to the external perturbations. This is very, very important to show the generalization boundaries and also at the same time the promise of your models to work in a less structured environment. And based on this predictive model, we train only with real data. The robot can use this model to solve inverse planning problem. And this inverse planning problems happening at two levels, both at the discrete level, what tool to use, and also at the continuous level, given the specific tool, what continuous action to take in order to progress into the next task stage. And all of these capabilities is actually benefited from this neural dynamics model to predict how the shape of the dough will change when you apply a specific action. Here's the most interesting part. When the robot will cut a circle out of the dumpling, the person shows no mercy, destroyed everything. And the robot knows it has to start from the very beginning, reduce the entire process. I would say this really shows the patience of our robotic systems in the face of these external perturbations. And we have also compared with physics-based simulators, material point methods. We realize even if we apply extensive system identifications using MPM, the neural dynamics model directly from the real data, because there's no sim-to-real gap, is noticeably more accurate than the MPM, even if we do system identification. And this has been the reason why we can allow the robot to do this very challenging task. And exactly the same a graph-based neural dynamics model can also be applied into many other object categories. We also show this model can be used to describe how the granular pieces will be moved around when you apply a specific pushing action. Then we take the model, pull the model into some model predictive planner, MPPI. We specify the target objectives. You probably have already realized what the target objectives are in this specific case. It's all different kind of letter shapes from letter A to letter Z. And the robots will be able to automatically coming up with the sequences of actions, obviously with feedback from the environments, to redistribute the object pieces into the target configuration. This is a very challenging task because it involves some non-trivial redistributions of the object pieces and some fine-grained alignments of the pieces distributions with the targets. We have also applied this graph-based neural dynamics model to multi-object interactions, where you can have some approximations of those objects and to use this graph-based neural dynamics model to describe their interactions, and also using this GPU-based graph-based neural dynamics model to do GPU-accelerated plannings for this kind of stowing tasks. And the end of the last year, we actually had a science robotics paper where we overviewed a series of work over the past decades on the directions of learning-based dynamics models for robotic manipulation. This paper also has some personal connection touches with me because the overall structure of the paper was built on top of the structure of my PhD thesis. This really is a deep reflections over a decades of understanding and investigations in what matters for the models to be useful that's learned from the real data that can be useful for robots to do manipulations. Highly recommended if you are interested in this direction. And then we are then asking the question, so what next? So now we have these spectrums. So what is actually the goal we should set for us to pursue this world model directions? So obviously, want to handle more complicated tasks and more complicated objects. And we also want to handle more heterogeneous type of interactions. And to also not just working in this kind of tabletop environment, but really scale up and benefited from all the large scale like data collection efforts people have been doing right now. Really, if you think about it, now people are spending huge amount of capital and time collecting demonstration data in the real environment. It is such a missing opportunity and such a waste if you only use that data for the imitation learning. There's such a rich information about the dynamics of the environment we should really leverage. So really going towards this scalable data engine and scalable evaluation engine through the directions of structured world models. So we're seeing like what is the right recipe that can really allows us to tackle and push this direction forwards. So one of the recipes we identified called PhysTwin is somewhere in between like a GBND and its more physics like directions. So what we are doing essentially is trying to build digital twins of the objects in the real environment. What we mean by digital twin is some kind of entity capturing the appearance, geometry, and dynamics of an object. What you're seeing here on the left are just a few seconds of real-world interactions in the real environment with the objects. In the middle, we are showing the reconstructed geometry of the object that are tracked over time. You probably have also noticed a number of red spheres on the human hands. That actually is representations of the human actions. On the right, we're actually having the foreground and the background. The background is the original video. The foreground is, like follow me, action conditions, open loop, 3D video prediction. That's what the foreground shows. We rendered the video from exactly the same viewpoints as the inputs video. You can see how well aligned the foreground is with the backgrounds. That shows the accuracy of our reconstructed digital twin. And this digital twin is actually built on top of also dense particles. Although in this case, we have more physics-informed priors to like regularize the relative motion between adjacent particles. And overall, we have, again, those three objectives over the geometry, over the motion, and over the rendering to reconstruct this digital twin. And after you have the digital twin, you can just randomly play with it with keyboard and mouse. It can help you to do this action conditions, 3D video predictions through the interactions with deformable objects, clothes, rope, etc. And I'm a roboticist, so I will always love to put my digital twin near my robots. What you're seeing here is just a person. My student Kaifeng, he's doing the tele operations of this like bimanual, like an X-arm setup. We record the action and replay the action in real times, both in the real environment shown on the bottom right, and also in our digital twin shown in the foregrounds of the screen. This is action condition open loop future prediction. And you can see this overlay that's really highlighted two things. One, this is very accurate. It's open loop future prediction aligns actually very nicely with what exactly happens in the real environment. And second, it is running in real time because we implemented everything like on GPU, so you can run at very high frame rates, like that's like synchronized with what actually happens in the real environment. And after we have this kind of setup, like I have like friends from Google, they reach out. They are like, can we actually use this digital environments to do evaluations of like robot policies? Because evaluation is such a huge pain for the people to iterate the robotic models. This is also one of the biggest difference between iterating the robotic foundation model and language-based foundation models. Because the iteration of the language-based foundation model only takes like GPU hours, like on the cloud, you can do it very fast. But the robotic foundation model iterations will need physical experiments, which is unsafe, hard to scale, and it's iterating at a speed that is multiple orders of magnitude slower than the iterations of the language like foundation models. I know Drew and Ali all have works on trying to do the evaluations in some kind of digital environments. So actually, my friends back then told me we have large enough budgets to still make progress. This was talking about this very earlier versions of Gemini robotics of doing tabletop manipulation tasks, which was, again, very, very impressive. But I'm pretty sure whatever they mean by progress can quickly diminishing when they move to like a larger scale and more complicated environments. So evaluation in the digital environments is actually a very essential thing for us to like furthering the developments. So what we did actually like in collaboration with Google was to have a streamlined pipeline. You take a phone, moving around the robots, You have the reconstructions about appearances and geometries of the robots, the environments, and also the objects you are going to interact with. And because there will be like color differences between the iPhone camera and RealSense camera, we also do like a color alignments, like between different kind of like a color spaces. We'll also take just a few seconds of real world interactions. And this few seconds of real world interactions we use to do the reconstruction of PhysTwin can also be used here in order to capturing the dynamics of the object. And this is actually the highlight. Here on the first row is the digital world, and the second row is the real environment. What you are seeing here is exactly the same robotic policies trained only with real data. We didn't do any co-training at all. The policy was trained only with real data. And just out of the box, the policy can behave in our digital environments in a way that has these state-of-the-art correlations with how it will behave in the real-world scenarios, especially, of course, not just rigid objects, but also deformable objects. Here's just some more closed-up view on how the rendering is looking like in our digital environments through the policy rollout procedures. So then, we compare the evaluation results in our digital worlds shown on the y-axis, and the evaluation results in the real environment shown on the x-axis over a number of different series of different checkpoints over 4 type of policies: ACT, DP, Pi0, and small VOA. You can see how strongly aligned and correlated they are with each other, whereas R value are all over 0.9. But there's one thing I want to highlight here. For any one of you who want to claim evaluation, you should be very concrete and specific in discussing the protocol you use to do the evaluation. So we take some of the best practices from Toyota Research, where they have trying to promote a series of practice for you to get the most clear signals through the evaluation procedures. So we follow a similar practice, and one of the most important practice is understand the distribution you use to do both the policy training and also the policy evaluations. So right now, I will always ask my students to show me this kind of overlays, both we use for training and use for evaluation. Otherwise, I'm telling them it's hard for me to build confidence in your results. So by showing me this kind of overlay and making sure you are resetting the environments according to the overlay. For example, here on the right, we are setting up the initial configurations according to some overlay shown on the left. It's making sure the evaluation's initial configurations are consistent between different checkpoints of the same policy, between different policy, and between the real environment and the digital world. That's the rigor we are taking in order to really tell people we have the correlation. And compare with, for example, Isaac, and show on the second row, because we have spent so much efforts aligning the dynamics and aligning the appearances. Our correlation is just so much better than the Isaac environment. And one of the side product you can do with this kind of correlation is to do a checkpoint selection. Here we're showing different combinations between task and the policy. The horizontal axis will be different training iterations, and the y-axis will be the success rate. We have curves describing the simulation results and the curves describing the real-world evaluation results. You can see they very nicely correlate with each other, where you can actually use the simulation evaluation to tell that the best performing checkpoints may not be at the very end, but somewhere in the middle. This is going to be very useful for you to do the iterations of the policy development. And right now, we have also been trying to digitalize not just stuffed animal and rigid objects. We're also digitalizing this elastoplastic articulated objects. Here on the top left is the simulation, and on the top right is the real world. I'm just telling you, this is on the top left, this is simulation, not animation. The simulation means the input to our digital environment are only the initial state and the subsequent actions. You can see how well aligned they are with each other. And in the bottom, on the left is the real world. On the right is the digital world. In the middle is the overlay. For this very long horizon, complicated manipulation task involving this kind of insertion of these 2 years into the 2 slots, you can see how well aligned they can with each other. So I have always trying to tell people, if you look at all the robotic application, it actually is working in the real environment. Planning drones, rockets, or Roombot, or even quadruped robots or bipedal robots. The reason why they are working is because you have a model. The model might be imperfect, but you have a model and you do sim to real transfer. Yes, manipulation is hard. Manipulation, because you don't only have to model the robots, you also have to model the environment. But that shouldn't be the reason for you not to try to model the environment. There are actually a lot of tools along the spectrums of learning and physics that actually allow you to do very, very precise modeling of the environment with the best correlations between the digital world and the real environment. That's just going to unlock so much potentials than just relies on the real data. And the last work I want to briefly discuss is actually our very recent work we released a few weeks ago on interactive world simulators. So basically, this is a work that is in between this kind of more learning routes and this GND, trying to use more learning-based priors to learn this kind of dynamics models. So basically, what we had is actually an action conditions video prediction models, where you are actually allow the teleoperators or human operator to do real-time interactions with these action conditions video predictions at 15 frames per second. And you can see this teleoperators motions is very, very stable, can do 15 hertz prediction over more than 10 minutes of future predictions. And this results actually to me is one of the first convincing results that really shows this action condition video predictions not only works for navigation, but also work in cases that involve complicated physical interactions with the environment. Of course, ropes, pushing T, granular manipulations, and also rope manipulations. What we did first was actually to use this model to do data generation. So this is what we actually do teleoperation in our world simulators. So we collected the demonstration data, trained the policy, and just 0 shots out of the box without any real data. The policy can directly work in the real environments at some very, very high success rates. And many people actually had the question, how much sim data is equivalent to one real data? So we actually did this study over a number of tasks, both in the simulated environments and also for real world tasks. And here you can see the x-axis. We vary the percentage of the data you use from the real and the percentage of the data from the world simulators. And we use exactly the same amount of data, and this different kind of mixtures between sim data and real data actually give you reasonably consistent performance across different kind of mixtures. And we can safely claim the digital data and the real data, they are sort of equivalents with each other. So this is actually very, very encouraging results. And right now I want to show a little bit of live demos of our digital environments. Here is actually our action condition video prediction that you can actually play right now on our websites. So the first task is actually pushing T. So what you need is to first connect with the server, and you can see I'm pressing on my keyboards, and this keyboard actually will be able to do the teleoperations of the synthetic robots in the digital world. It is able to do a very stable and long horizon prediction in the real times. You can also see the highlights of the keyboards. That is the key I just pressed. So there is actually some bit of a latency because of the internet issue, but overall you get the points of how we can do very precise long horizon future prediction. And the second example is actually a bimanual rope manipulation. You can actually lift the arm up and also move it down. Okay, okay, there's some artifacts. Shows you this is actually video prediction instead of video recorded somewhere else. And you can actually try to route this rope inside, and we can move it down and move it up. You can see the rope can successfully being clicked there. You can also see during the teleoperation, the person in the back is also somewhat being teleoperated by me. This is actually this very interesting observation we had. You can actually teleoperate an old versions of yourself. So this is actually very interesting teleoperators you can actually play with. So going towards the ends, obviously the last missing piece goes without saying is about the data. Our lab has also been involved in a number of large-scale data collection initiatives, both in the real environments through these OpenX embodiments, and also in collaborations with the behavior teams at Stanford Vision and Learning Lab to also scale up the digital and simulation data. We have also been collecting multimodal data of like a human's kitchen activities by considering visual information, like tactile information, human body information, like a muscle signal information, audio information, etc. And obviously, what I just showed of using this portable multimodal gripper to the large scale like data collection that consider not only the vision, but also the touch. So in the end, I want to highlight like what I mean actually by this kind of foundational robotic capabilities. Actually, draw some inspiration and similarities with other people. If you look at the current foundational vision and language models, the output may not always be perfect, but it will always be able to generate something that is reasonable and plausible given the inputs. So what I hope to achieve with this kind of more foundational robotic capabilities is that the synthetic action may not always be the optimal action, but to always be able to generate the actions that are beautiful and reasonable when you execute in the real environment, and allow the robot to work across a wide range of tasks that go beyond just fully structured environments, but into semi-structured environments and unstructured environments. I want to thank all the collaborators, especially my students. Without them, it would be impossible to do all the tasks, and also the funding agencies. And that comes to the end of my talk. Thank you so much.
We have time for a few questions. Just two quick announcements first. Number one, if you're here for the robotics minor, make sure that you fill out the form on the seminar webpage while you're sitting in this room. Number two, everyone's welcome to join us for robotics lunch after this back in the F-wing. All right.
For the word model part, you have two lines. One is use the 2D pixel, which is video prediction. Another is use 3D observation. It's like point cloud based to learn the word model. My thinking is that my question is that what has in the future, which observation space will play a more important role? Because for 2D we have more pre-trained model on their side, but for 3D it has the physical consistency, which they have some different advantage and disadvantage. So in your view, which will be more important for the future?
So that is very good questions. So to be honest, I don't have a good answer. I don't have a conclusive answers like right now. So that is why I was showing this kind of spectrums over both the learning and also over the physics. So this is because I see a lot of benefits of like both camps, where if you have some more structured representation of the environment, it's so much easier to add geometric priors or physics-based priors or some other structured priors. But obviously with like a pixel with videos, it's easier to like benefit from all the data out there. But there's also a lot of nuances depending on whether you have access to the action labels in those videos. But nevertheless, so right now, I don't think I know the right answer. I don't think I know the right recipe. So that's why we are actually investigating and actively like betting on different like points along this spectrum and to see which one gives us the best scalability and the levels of accuracy that's needed for the benefits of robots. But having said that, even if we don't know the recipe, but we should know how we should evaluate them. And the way I'm right now thinking about the evaluation is really through this data engine and also evaluation engine. So if this model is useful for me to generate the data for the model training or be able to do the evaluation, tell me and distinguish between a policy that is 90% success and another policy that is 92% success, those will be the metric I will apply to the word models that we are developing.
Yeah, thank you for the talk. I'm very curious about policy evaluation. Like, from my understanding, a lot of work has the metric that is a correlation between the success rate in both the simulation and real world. So I have a question: is that have you ever observed some similarity between the failure mode in the simulation environment?
That is a very good questions and also more nuanced questions. So right now, like we have this kind of correlation, which is great. But we do actually observe a decent amount of false positives and false negatives. So meaning like if in the real environment, this is a success trial, but it can fail also in the digital world. And there's also failures like successes in the digital world, but that end up to be failures in the real environment. We have observed those cases. Although that's a small percentage, but those are the cases that I believe we should spend like more efforts like going forwards, because that's really is actually going towards the directions on how you can do faithful reconstructions of the failures in the digital world such that you not only can do the re-simulations of the failure cases, but also do like data augmentations near that's like a failure, like a data points for you to have more robust coverage of your like a state space. So very good questions, and there's actually a lot of nuances along that area.
Yeah, because like from my understanding, a good analysis of failure cases what brings you to the success of real world policy. So like if the simulation evaluation can give you a very good reason about why you possible fail in that simulation environment, then maybe this is very useful for the real world policy.
Yeah, that's very good. Actually, in the interactive word simulation paper, we actually successfully using our action condition video prediction models to find bugs of our like a policy implementations. This is actually was very useful. So yes, it can actually help you to do the debugging and iterations of the policies. But we still, like I have to admit, we still observe false positives and false negatives. And that's actually a very active directions of research that we are right now doing in my lab. Yeah.
Thanks for the great talk. Question on evaluation. So you showed this slide. You said we want to see what is the initial distribution, real versus sim, before you start doing evals. And then the slide was about like, yeah, exactly this. So this is the training initial state distribution, real. So in the digital twin in your simulator, if you try to eval, right now these kind of match really well, but if you try to go outside this training initial state distribution, do you still notice a high correlation, or what observations?
So very good question. So there's some nuances around those. So in this case, if you, for example, move your like slots like a very outside of the, for example, training distributions, like the policy will do like a very weird stuff. So like and the policy will do weird stuff like both in the real environments and also in the digital environments. But our digital environments will still be like fine, because it's built on top of this kind of physics informed like modeling of the environments. The generalization of the dynamics like modeling capabilities will still be very, very decent. It's just the policy can behave in a very weird manners. So what we observe, especially at the very beginning of the training sequences where the policy like generates like random behaviors, we see like failures that are very arbitrary, like both in the real environment and the simulated environment, meaning they will both be failures, but they can fail in like a slightly different ways. Because when the robot is not when the policy was not very well trained, the output may be sometimes very discontinuous. You have some kind of very like a heavy like a vibration, like movements that will actually shake the entire table. But in the simulation, it won't shake the table. So meaning like our simulation can tell it is a failure. But what we observe is actually as the policy have better and better performances, and the correlation between the failure patterns will become like closer and closer. Does that answer your question? Yeah. Because of those kind of unmodeled crazy behaviors of the policy that might happen in the real environment.
The detailed question on slide number 88. You were showing this box folding, and you indicated that you are simulating this elastoplast behavior. I'm just so curious about like in your physical model, how do you take care of this history-dependent model? Because, for example, if this the paper has some plasticity, when you load and unload, the stiffness may change. I'm just wondering how do you take care of that?
Very good question. I can actually like expand quite a bit on this point, but I will keep it short. So in this like modeling, we actually have parameters that describe the fatigue of the joints. So the fatigue parameters can change, like that will change the plasticities, like describe the plasticities of this kind of models. So what you are seeing here is that we take the sequence, we do resimulation. So basically we take this sequence and estimate the parameters that are specific to this sequence. But in practice, in the real world, when you're actually trying to apply this kind of models, what you need is not just one single data point. What you need is the distributions of those parameters, such that you'll be able to obtain a policy that is robust to all the data points within that distribution. So here we're just showing like one single data point where we have this particular parameters that are changing, that time varying, like varying over times. But in practice, for you to actually use this kind of digital environments, it's a distribution that you should care about the most, and we are working on that. Yeah.
All right, maybe one more question.
Talking about the spectrum from more physics ended to more learning
world model, I'm sort of wondering what your intuition is on what side is more valuable, especially in the future and how it evolves for evaluation. Because just from looking at the interactive world simulator, it seems like the results that you're getting when you're putting in your action tend to aggregate towards like the result of the task, right? So like the rope, even if the rope isn't particularly close to the like pins that you're going for, it'll kind of push in that direction, and maybe the block will move away from the other arm so that it doesn't like merge with it because it's avoiding things that it hasn't seen before in that training distribution. So I'm wondering, like, is there a way to fix that without physics? Can you reliably create something just visually and maybe with action conditioning that's still valuable for evaluation, or do you have to sort of depend on the physics?
So very good questions. I want to respond to from two axes. The first axis is about some kind of biases actually in the data. This is something I want to highlight. So this model was only trained with 6 hours of data collections, by my students Yishuan, in the real environment. And thinking about if you just 10 times that data, 100 times that data, and 1,000 times of that data, that is something that is very plausible to do nowadays in the industry. It may not be the most plausible thing to do in the lab, but that's something can be done. And if you have a more better coverage, because this data actually collected through play data, not through task-specific data. It's through play data. So it actually can have better coverage to learn a model that is slightly less biased. This is actually where I think the division between academia and industry should be. So we're in academia. We're showing you, hey, there's a new ways of doing scaling. And we show you the initial segments and the promise of you scaling things up. And I think it will be the industry job, either through collaborations or through any other means, to further extrapolate over that curve to see what happens. But I wouldn't think bias is the most like a dire issue, because I believe at least in those scenarios we can collect the data that give better coverages. But how to extend this to have some more controllability is something that we feel actually is the limitations of this. For example, now you are changing new objects, you change the friction, you change your different embodiments, or you want to, for example, do a simulations of another environment with the surfaces of different frictions. What happens then? If you have to do some kind of identification of the parameters, those are the limitations we actually see to be more dire right now, the controllabilities of this kind of models. And then on the other hands about do you have another? What was the other points? Let me try to remember.
I'm mostly wondering about which one is more valuable for evaluation.
Oh yeah, yes. Now I remember. So because we have been using this model for both policy training and also policy evaluation, we also realize some kind of nuanced difference between the importance of visual fidelity and the importance of dynamics fidelities for both training purposes and evaluation purpose. So as we realize for evaluation purpose, visual fidelity is very, very important. But the dynamics fidelity may not be as important. The reason I claim that is because typically the policy you want to do the evaluation are already policies that give you decent performance. You want to distinguish between 90% success rate and 92% success rates. So such that you want to making sure it's already in a regime where the robots won't do crazy discontinuous stuff that will shake the table. But for the training, the visual fidelity may not matter as much because you can do a lot of randomizations on the vision side. But the dynamics actually, we would argue, can matter more because you possibly want to do reinforcement learning in the digital environment. You want to make sure your simulator or digital world or whatever is harder to be exploited by your reinforcement learning agents. So on that front, I would argue dynamics fidelity will be more important. So there will be nuances. That actually goes back to your questions. Depending on whether you want to use the model to evaluation or whether you want to use the model to do training, there will be slightly different considerations of whether dive into the video prediction routes or more structured route. Does that answer your question?
All right, let's thank you, Steve again.
本文章已收录至雷锋网 ACRA 2026深度专区，现已全面上线。专区不仅全面收录了重磅论文的工程化解读、专家前沿演讲，更将持续更新前方记者的第一手会议动态。扫描下方二维码或进入雷锋网 ACRA 专区即可查看。